Welcome to the Deep Dive. Today, we're really embarking on a mission. We want to cut through all the complexity of modern software systems, the tech you interact with every single day.
Right. There's so much happening behind the scenes.
Exactly. And you've shared a ton of great insights with us. Our goal here is to pull out the really important nuggets of knowledge, give you a shortcut, basically, to being truly well-informed.
It's about pulling back that curtain, isn't it? Seeing how the digital world really works.
Totally. From the tiniest bits and bytes right up to the huge systems behind your favorite apps. Get ready for, hopefully, some surprising facts and maybe a few aha moments along the way.
Sounds good. Where should we start?
Okay, let's peel back the very, very first layer. Have you ever stopped to think how computers actually store numbers? Like at the most fundamental level?
Probably not in detail for most people.
Right. It comes down to something called byte ordering, or sometimes people call it endianness or endian nature.
Yeah, NDNS.
Essentially, when you have a number, say a big integer, that needs more than one byte of memory to store it. Well, the order those bytes are arranged in memory actually matters a lot.
It really does. And there are two main ways this happens.
Little endian and big endian. So with little endian, and this is common in processors you find everywhere, like Intel by 86 chips, the least significant byte gets stored first, at the lowest memory address.
Think of it like writing down a multi-digit number, but you write the last digit first, then the second to last, and so on. Then you store it that way in memory.
That's a great way to picture it. And the opposite.
That's big endian. Here, the most significant byte, the biggest part of the number, is stored first, at the lowest memory address. This is pretty common in network communications. Lots of standard file formats use it, and older architectures like PowerPC were big on it too.
So why does this, tiny detail matter so much?
Well, it becomes incredibly important when data moves between different systems. Imagine one system writes data out using little endian, and another system tries to read it, but it assumes the data is in big endian.
It's going to read it completely wrong.
Exactly. You get total garbage, garbled, meaningless information. So handling this byte order correctly is absolutely foundational if you want different computer systems to talk to each other and understand the data consistently. It stops your data getting lost in translation, basically.
Okay, that makes sense. So, building on these fundamentals, let's talk memory.
Memory. What's fascinating here and really critical to understand is that memory isn't just, one big container. It's actually a hierarchy.
A hierarchy, like levels.
Precisely. It's structured in layers, very carefully designed to balance cost, size, and crucially, the need for super fast data access.
Okay, walk us through these layers, top level.
At the very top, literally inside the CPU itself, you have registers. These are incredibly tiny, but ultra-fast storage spots. They're for data the CPU needs, like right now.
Like having your most important tool strapped to your wrist.
Exactly. Then, just a tiny step away, physically very close to the CPU, you find the caches, usually L1, L2, maybe L3.
L1, L2, L3, I've heard those terms. They're faster than regular RAM, right?
Much faster. They're small, quick memory blocks whose whole job is to speed up data retrieval. Think about it. Getting data from L1 cache might take just 1 nanosecond. L2, maybe 10 nanoseconds.
Wow. Okay. And compared to main memory?
Main memory, your RAM, might be around 100 nanoseconds. So L1 cache is roughly, 100 times faster? It's the difference between having tools on your workbench versus walking across the factory floor to get them.
Gotcha. So after caches comes the main workhorse.
Your main memory, or RAM, yes. That's the larger primary storage area for all the programs and data that are actively running. Access time's around 100 nanoseconds, like we said.
Okay. And then we get into storage that sticks around even when the power's off.
Right, persistent storage. First up, you have solid-state drives, SSDs. They're fast, reliable, because they have no moving parts. Read times are maybe around 100 microseconds. Notice that's microseconds, not nanoseconds.
Still way faster than the old spinning disks, though.
Oh, absolutely. Those are next. Hard disk drives, HDDs, the traditional mechanical drives, they offer huge capacities for long-term storage, but they are significantly slower. Think milliseconds for access time.
And the final layer, way out there.
That would be remote secondary storage. Think network drives, cloud storage backups, archival systems, accessible over a network, much slower, but essential for backups and storing vast amounts of data you don't need instantly.
So it's this whole tiered system, this hierarchy, balancing speed, size, and cost.
Exactly. It's a really sophisticated trade-off that lets your computer do everything from complex calculations to just browsing the web smoothly.
Okay, so we have data ordering with endianness and this memory hierarchy. How does this all come together when you, say, double-click an icon to run a program? What actually happens?
That double click kicks off a surprisingly complex dance, all orchestrated by the operating system, the OS.
It's not just poof, it runs.
Not quite. First, when you signal you want to launch that app, the OS has to find the program's executable file. It retrieves it from the file system, your hard drive or SSD,
Okay, finds the file.
and then it loads that file into main memory, into RAM.
But wait, most programs need other stuff too, right? Like libraries.
Absolutely. Most modern apps rely on shared libraries. Think of them as common toolkits. On Windows, they're often DLLs. On Linux, maybe .so files.
So the OS needs those too.
Yes. It needs to figure out which shared libraries the program depends on, that's dependency resolution, and load those into memory as well. This saves space because multiple programs can use the same library code.
Smart. Okay, program loaded, libraries loaded. What's next?
Then the OS allocates dedicated memory space just for this program. It carves out a section of RAM for the application's code, its data, its stack, everything it needs to run.
Gives it its own little sandbox?
Sort of, yeah. And after that, the OS and maybe a specific runtime environment, like if it's a Java program, the Java virtual machine, or JVM, they initialize any other necessary resources, setting things up.
Okay, everything's prepped. Showtime.
Sure time. The program's official entry point, usually a function called main, gets called. And from that moment, the CPU starts fetching instructions from the program's allocated memory and executing them, one after another.
And it grabs data from memory too.
Yes. This is the key to the von Neumann architecture, which pretty much all modern computers use. Instructions and data live in the same memory space, and the CPU fetches both as needed. It's what makes computers so flexible and general purpose.
Right, that was a huge breakthrough.
A massive one. And this cycle, fetch instruction, decode, execute, maybe fetch, store data, continues until the program finishes its job, or until you tell it to close.
And when it closes, does it just vanish?
Not quite. There's a cleanup phase. A well-behaved program will release resources it was using, like closing any files it had opened, freeing up network connections, and critically telling the OS it's done with its allocated memory so it could be used by other programs.
Wow. Okay, that's quite a process happening behind that simple double click.
It really is. Thousands of times a day on your computer, probably, without you even noticing.
All right, so we understand a bit more about what's happening inside one computer. Now let's zoom out. How do these machines talk to each other across the internet? The web specifically.
The web. Yeah, the fundamental language there is HTTP, Hypertext Transfer Protocol.
And you mentioned something surprising about it. It's stateless. What does that mean?
Stateless means that by its very nature, each HTTP request is independent. The server handles a request, sends back a response, and then it completely forgets who you are.
It forgets you instantly. So how does anything work? How do websites remember I'm logged in or what's in my shopping cart?
Exactly. If HTTP was all we had, the web would be unusable for anything complex. That's where our unsung heroes come in. Cookies?
Cookies, not the edible kind, I assume.
No, definitely not. Think of web cookies as tiny little notes or maybe identification tags that a web server asks your browser to hold on to.
Okay, notes from the server.
When the server sends you a web page, it can include a set cookie header with a small piece of data. Your browser stores this note. Then, the next time your browser makes a request to that same server,
It sends the note back.
precisely, it includes the cookie in the request header. The server reads the note and goes, I remember you. You're the user who logged in, or you're the one who put those items in the cart. Cookies add that memory, that state, to the otherwise stateless HTTP.
That's actually quite clever, like little session IDs or preference reminders.
Exactly, and browsers are pretty strict about this. They act like secure cookie messengers, only sending a cookie back to the specific website domain that originally set it. They won't just hand out your cookies to any site that asks.
Security is obviously key there.
Hugely important, and cookies have attributes to help with that, like HTTP only, which is a flag telling the browser that the cookie should not be accessible via JavaScript running on the page.
Why is that important?
It helps block a common attack called cross-site scripting, or XSS, where attackers try to inject malicious scripts to steal sensitive cookies, like your session ID. If it's HTTP hero, their script can't grab it.
Okay, that makes sense. Any other important attributes?
Another big one is same site. This attribute helps control when a cookie is sent with requests initiated from other websites. It's a key defense against cross-site request forgery or CSRF attacks, where an attacker tries to trick your browser into making a request to a site you're logged into without you knowing.
Wow. So cookies aren't just about convenience, they're deeply tied into web security, too.
Absolutely fundamental.
Yeah.
They enable the seamless, personalized web experience we take for granted, but they also need careful handling to keep things secure.
Okay, sticking with communication. When developers are building applications, especially modern ones with lots of different parts, how do those parts, those services, talk to each other? I hear about APIs all the time.
Right. APIs, application programming interfaces, are the contracts that define how software components interact. And in the web world, two major design approaches have really shaped things: REST and GraphQL.
REST and GraphQL. Okay, let's break those down. What's REST?
REST stands for Representational State Transfer. It's been the dominant approach for a long time. It leverages the standard HTTP methods you already know: get to retrieve data, post to create, put to update, delete to remove.
So it kind of uses the web's existing language.
Exactly. It treats things as resources like users, products, posts, and you use these standard verbs to operate on them via unique URLs. It's generally pretty straightforward, especially for simpler interactions, and caching responses is often relatively easy with standard HTTP caching.
Sounds pretty good. What's the catch?
The main challenge, especially with complex applications, can be what's called overfetching or underfetching.
Meaning?
Overfetching means you call an endpoint, say, to get user details, and it sends back everything about the user name, email, address, posts, comments, even if you only needed their name. Lots of wasted data.
Okay, and underfetching.
That's when you need data that spans multiple resources. Like, you need details about an author and their latest posts and the comments on those posts. With REST, you might have to make 3 separate requests to 3 different endpoints to gather all that information. Multiple round trips.
Ah, I see. That could be slow and inefficient.
It can be, and that's where GraphQL comes in as an alternative.
So how does GraphQL solve this?
GraphQL provides a single endpoint. Instead of multiple URLs for different resources, clients send a query to this one endpoint, specifying exactly the data fields they need, even across related resources.
Like making a specific shopping list instead of just asking for groceries?
Perfect analogy. You send a query that might look like, get me the author with ID 5, and for that author, just give me their name and the titles of their last 3 posts. The server processes this query and sends back a JSON response containing only that requested data, usually in a single round trip.
So no overfetching, no underfetching. That sounds way better.
It's very efficient for the client and reduces network traffic. GraphQL also natively supports mutations for changing data and subscriptions for real-time updates like live notifications. It's incredibly flexible, especially for complex front-end applications. Companies like Netflix use it heavily.
But there must be trade-offs, right? It can't be perfect.
Of course. With GraphQL, more complexity shifts to the server side to resolve these complex queries efficiently. You also need to be careful about abusive queries. Someone could potentially craft a deeply nested query that hammers your backend if you don't put safeguards in place, like query depth limiting or cost analysis.
Ah, security and performance concerns.
And caching can be more complex than the standard HTTP caching used with REST, because you have one endpoint handling many different types of queries. So yeah, pros and cons. The choice really depends on the specific needs of your application.
Okay, that distinction is much clearer now. So whether it's REST or GraphQL or just users hitting a website, there's a ton of traffic flying around. How do large systems manage all that flow?
Right. Managing that flow efficiently and securely is crucial. And there are 3 key players you often find working together: reverse proxies, API gateways, and load balancers. They sound similar, but they have distinct roles.
Okay, let's untangle them. Start with reverse proxy.
A reverse proxy sits in front of one or more web servers. From the outside, it looks like the actual server. When a request comes in, the reverse proxy forwards it to the appropriate backend server, gets the response, and sends it back to the client.
So it acts like a front man hiding the real servers.
Exactly. That's a major benefit security. It shields your backend servers from direct internet exposure. But it can also handle tasks like SSL encryption-decryption, compressing responses, caching static content, and sometimes even basic load balancing. Think of it as the secure gatekeeper and initial handler for your web property.
Okay, gatekeeper. What about the API gateway then?
An API gateway is often the next layer in, especially in microservices architectures. While a reverse proxy deals with general web traffic, an API gateway is specifically designed as a single entry point for API calls.
So it's like the central dispatch for all the different API services running behind it.
Precisely. A client makes one call to the API gateway, and the gateway then routes that request to the correct backend microservice, or sometimes even aggregates responses from multiple services. But it does much more than just routing.
Like what?
Crucially, it handles things like authentication, who are you?
Uh-huh.
Authorization, what are you allowed to do? Rate limiting to prevent abuse, request response transformation, logging, monitoring, and sometimes caching API responses. It's the central control point for your APIs.
Got it. Sort of like the highly organized mailroom and security checkpoint for all API requests.
That's a good way to think about it.
Okay, one left. Load balancer. This one sounds like its name.
It does. A load balancer's primary job is to distribute incoming network traffic, whether it's general web traffic or API calls across multiple backend servers.
Why spread it out?
To prevent any single server from getting overloaded, this improves performance, ensures scalability, you can add more servers as traffic grows, and increases reliability.
Reliability how?
Load balancers constantly check the health of the servers behind them. If one server becomes unresponsive or fails, the load balancer automatically stops sending traffic to it and reroutes requests to the healthy servers. This provides high availability, keeping your application running, even if some servers go down.
So it's the traffic cop, directing requests to keep everything flowing smoothly and handling detours if there's an accident.
Excellent analogy. And importantly, these roles often overlap or work together. An API gateway might include load balancing features. Both API gateways and load balancers often sit behind a reverse proxy for that initial layer of security and handling. They're a team.
A super team, keeping the digital world running. Okay, that makes a lot more sense. Now, you mentioned caching several times. Reverse proxies cache, API gateways might cache. Caching seems vital for performance.
Oh, it's absolutely critical.
Yeah.
But it's also a double-edged sword. When caching goes wrong, it can cause some really significant problems.
Okay, let's talk pitfalls. What can go wrong with caching?
One classic issue is the thunderherd problem, or sometimes called cache stampede.
Thunderherd. Sounds dramatic.
It can be. Imagine you have a popular piece of data in your cache and its expiration time is set. When that time hits, the cache entry is invalid. If lots of users request that data right then, bam, they all miss the cache simultaneously and rush straight to your primary database to get the fresh data.
Like a stampede overwhelming the database?
Exactly. The database gets hammered, potentially slowing down or even crashing.
Ouch! How do you prevent that stampede?
A couple of ways. You can add a bit of randomness or jitter to the cache expiration time, so not everything expires at the exact same second. Or you can implement locking mechanisms where only the first request that misses the cache goes to the database to refresh it, while subsequent requests wait briefly for the cache to be repopulated. Another strategy during recovery is to only let critical requests hit the database.
Okay, makes sense. What else can go wrong?
Another common one is cache penetration. This happens when requests come in for data that doesn't exist, not in the cache and not even in the database.
Like someone's searching for a product ID that was never created.
Precisely. If you're not careful, every single one of those requests for non-existent data will bypass the cache and hit your database, asking, do we have this, over and over. It's a pointless load.
How do you stop that?
Two main techniques. One is simple. Cache the fact that the data doesn't exist. You store a special null value or marker in the cache for that key for a short period. The next time someone asks for that non-existent key, the cache says, nope, doesn't exist, and the database is protected.
Ah, cache the negative result. Clever.
The other technique is using a Bloom filter. This is a fascinating, space-efficient, probabilistic data structure.
Probabilistic.
Yeah, it can tell you with certainty if an item is definitely not in a set. Or it might say the item is probably in the set, with a small chance of being wrong. It's a false positive. You can keep a Bloom filter of all valid keys in front of your cache. If a request comes for a key, you check the Bloom filter first. If it says definitely not here, you reject the request immediately without hitting the cache or the database.
Wow, okay. That sounds efficient for filtering out garbage requests.
Very much so. Then there's cache breakdown. This is similar to the thunderherd, but focuses on a specific hot key, a piece of data that's accessed extremely frequently.
Like the homepage content or a viral product.
Exactly. If that hot key expires, suddenly a massive number of requests that were hitting the cache now flood the database simultaneously.
So for those super popular items.
The simplest solution is often just don't set an expiration time for those specific hotkeys. Or use a system where the cache proactively refreshes the hotkey just before it expires.
Keep the really important stuff permanently or almost permanently cached.
Right. And the final, most scary scenario is cache crash. The whole cache system, maybe your Redis cluster or memcached instances, goes down.
Uh-oh. Then everything goes to the database.
Everything. Instant database overload, likely taking your application down with it.
Nightmare scenario. What's the defense?
A couple of key strategies. One is implementing a circuit breaker. This is a pattern where your application monitors the health of the cache. If it detects the cache is down or timing out, the circuit breaker trips or opens, and the application temporarily stops sending any requests to the cache, and thus stops them cascading to the database. It fails fast, maybe returns an error or stale data, giving the cache and database time to recover without being overwhelmed.
Like flipping a breaker switch in your house to prevent further damage.
Exactly. The other, more fundamental solution is high availability for the cache itself. Don't rely on a single cache instance. Set up a cache cluster, like Redis Sentinel or Cluster, so if one node fails, others can take over. Build in redundancy.
So lots of ways caching can bite you, but also smart ways to protect against it.
Definitely. It requires careful design and monitoring.
Okay, so protecting the database from cache issues is one thing, but what about when the database itself just can't keep up with the sheer volume of data or traffic? How do you scale databases? It's not just buying a bigger server, is it?
No. Throwing more hardware at it, vertical scaling, meaning adding more CPU, RAM, or faster storage to a single server, is often the first step. But you quickly hit limits or prohibitive costs. True database scaling involves a whole toolbox of techniques.
Okay, what's in the toolbox besides a bigger server?
Well, first, optimization. You absolutely need to optimize your queries. Indexing is fundamental. Creating the right indexes on your tables is like creating a super efficient index in the back of a book. It lets the database find the data it needs much, much faster without scanning everything.
Makes sense. What else?
Materialized views. If you have complex queries that join lots of tables or do heavy calculations, and the results don't need to be absolutely real-time, you can pre-compute the results and store them in a special table called a materialized view. Queries against this view are then super fast.
Like pre-calculating report summaries overnight.
Exactly. Another optimization, though sometimes controversial, is denormalization. This involves strategically breaking the rules of database normalization by adding redundant data to tables, specifically to avoid costly joins when reading data. You trade some storage space and data consistency complexity for faster read performance.
So optimize first, then what?
Then you start distributing the load.
Yeah.
We already talked about caching. Putting a system like Redis or Memcached in front of the database to handle frequent reads is a huge load reducer.
Right. Offload the easy stuff.
Then there's replication. This is huge for scaling read traffic. You set up one primary database server that handles all the writes, inserts, updates, deletes, and then you create one or more read replicas copies of the primary.
Copies.
Yeah, the primary database continuously sends its changes to the replicas, keeping them nearly up to date. You then direct all or most of your application's read queries to these replicas. This spreads the read load across multiple machines, freeing up the primary server to focus on writes.
Okay, so replication handles lots of readers. But what if you have tons of writes too, or just an enormous amount of data?
That's where sharding, or horizontal partitioning, comes in. This is usually the most complex step, but it's how you scale both reads and writes almost indefinitely.
Sharding, like breaking glass.
Kind of.
Yeah.
You split your database, often one or more large tables, into smaller, independent pieces called shards. Each shard contains a subset of the total data, e.g. users AM go to shard 1, users NZ go to shard 2. These shards are then stored on separate database servers.
So you're splitting the data and the traffic across multiple servers.
Exactly. When a query comes in, your application or a proxy layer needs to figure out which shard holds the relevant data and route the query there. This distributes the load significantly, allowing you to handle massive data sets and transaction volumes.
That sounds powerful, but also complex to manage.
It absolutely is. You need logic to route queries, handle cross-shard operations, manage schema changes across shards. It's a big architectural step.
You mentioned Figma earlier, scaled Postgres 100x. How did they do it? Do they use all these?
They used a combination, which is typical. They started with vertical scaling, getting the biggest Amazon RDS instance. Then they hit limits. They added PG Bouncer, a connection pooler, to handle the sheer number of connections efficiently, which is a form of optimization.
Okay.
Then they implemented vertical partitioning. They identified high-traffic tables, like the main Figma files table, and moved them to entirely separate physical database instances, like giving the busiest department its own building.
Ah, splitting by table function.
Right. And then, when even those separate databases grew enormous terabytes large, they implemented horizontal partitioning, or sharding. They split those massive tables across multiple physical databases based on sharding keys and built their own DB proxy service to route requests to the correct shard.
Wow, so it was a journey. Scale up, optimize connections, split vertically, then finally shard horizontally.
Exactly. It shows that scaling is often an iterative process, applying different techniques as you had different bottlenecks.
Okay, so we've scaled our database, maybe we're running in the cloud, but what happens if disaster strikes? Like a whole data center goes offline. How do you recover?
That's where cloud disaster recovery planning comes in. And it really revolves around two key metrics you have to define for your application.
Two metrics.
Yep. First is RTO, recovery time objective.
Yep.
This is the maximum acceptable amount of time your application can be offline following a disaster. Is it okay if it takes 4 hours to come back, or does it need to be back in 5 minutes?
How quickly you need to recover. Got it. What's the second?
RPO, recovery point objective. This defines the maximum acceptable amount of data loss measured in time. Is it okay to lose up to an hour's worth of data entered before the disaster, or can you only afford to lose, say, the last 5 seconds of data?
How much data you can afford to lose. Okay,
Yeah.
RTO and RPO.
Exactly. These two numbers fundamentally drive your disaster recovery strategy and, importantly, its cost. A very low RTO and RPO, meaning fast recovery, minimal data loss, is much more expensive to achieve.
So what are the common strategies based on RTOR ERPO?
At the most basic level, you have backup and restore. You take regular backups, say daily or hourly, and store them somewhere safe, maybe in a different region. If disaster strikes, you provision new infrastructure and restore from the latest backup.
What are the RTOR ERPO like for that?
RTO is typically hours, maybe even days, depending on the complexity. RPO is determined by your backup frequency. If you back up hourly, you could lose up to an hour of data. It's the cheapest option, but the slowest recovery.
Okay, what's a step up?
The pilot light approach. Here you have the core infrastructure, maybe the database servers or critical app servers running in a standby region, but scale down or turned off. You replicate data continuously. If disaster hits, you turn on the pilot light, scale up the infrastructure, switch DNS, and you're back online faster.
Faster RTO then.
Yeah, RTO is usually minutes to hours. RPO can be quite low depending on how frequently data is replicated, maybe minutes or seconds. More expensive than just backups, obviously.
Getting warmer.
Next is warm standby. This is similar to pilot light, but the standby environment is running, scaled down but active, and continuously receiving data updates. Recovery involves scaling up the infrastructure and redirecting traffic.
Even faster recovery?
Generally, yes.
Got it.
RTO is often measured in minutes. RPO remains low, similar to pilot light. It's a balance between cost and recovery speed.
And the top tier for
Absolutely.
critical systems.
That's the hot site or multi-site strategy. Here, you have a fully operational duplicate environment running in parallel in a separate region, actively serving traffic alongside your primary site, maybe in an active setup, or ready to take over instantly, active-passive.
So it's like having a complete clone ready to go.
Exactly. Data is replicated in near real time. If the primary site fails, traffic is automatically rerouted to the hot site. RTO is almost immediate, maybe seconds to minutes. RPO is extremely minimal, potentially zero or just a few seconds of data loss. But as you can imagine, this is the most complex and expensive strategy as you're essentially doubling your infrastructure costs.
Right, so it's a clear trade-off. Faster recovery and less data loss equals higher cost and complexity.
Precisely. You choose the strategy that meets the specific RTO and RPO requirements for your application and budget.
Okay, fascinating stuff on resilience. Let's shift gears a bit now, maybe look inside the developer's world. Let's talk about Git. Most people know it for saving code versions and collaborating.
Right. Git is indispensable for modern software development.
But you mentioned something interesting. There are actually 4 locations code lives in when using Git. I usually just think of my computer and like GitHub.
That's the common view, but yeah, technically, Git manages things across 4 distinct areas. 3 of them are right there on your local machine.
3 local areas. Okay, what are they?
First, you have your working directory. This is just the project folder on your computer where you're actually editing the files. Your active workspace.
Okay, where I type the code. Easy enough.
Second, there's the staging area, sometimes called the index. This is like a temporary holding bay. When you make changes in your working directory, you use git add to move specific changes into the staging area.
Why stage them? Why not just save directly?
The staging area lets you craft your next commit precisely. You can stage changes from multiple files or even parts of changes within a single file to group related modifications together into one logical snapshot, one commit. It gives you control over what goes into the history.
Okay. Like packing a box carefully before sealing it. So working directory, staging area. What's the third local spot?
That's your local repository. This is where Git stores all the committed snapshots of your project, the entire history, right there on your machine in that hidden .git folder. When you run git commit, The changes from the staging area are permanently saved as a new snapshot in your local repository.
Got it. My personal history of the project. And the fourth location is the obvious one.
Yeah, the fourth is the remote repository. This is the shared server, like GitHub, GitLab, or Bitbucket, where you and your team push your committed changes to collaborate and back up your work.
So, working directory staging area, local remote repo?
Pretty much. And most basic Git commands are just about moving changes between these four locations. Git add moves from working to staging. Git commit moves from staging to local repo. Git push sends commits from your local repo to the remote repo. Git pull fetches changes from the remote repo and merges them into your working directory, usually via your local repo.
Huh. Thinking about it that way actually makes Git commands seem simpler. It's just moving stuff between these four boxes.
It's a really helpful mental model, yeah. Demystifies it quite a bit.
Okay, so developers use Git to manage their code. Now, how does that code get from their machine through all that Git stuff and actually into the hands of users, the journey to production?
The deployment pipeline. In most modern software companies, this is a highly structured, often automated process, usually referred to as CI/CD.
CI/CD. Continuous integration and continuous delivery or deployment.
Exactly. It starts way before the code, really. Product owners define features, often as user stories, based on business needs or user feedback. These stories go into a backlog.
Okay, the wish list.
Then the development team picks stories from the backlog, usually planning them into a sprint, which is typically a fixed period, like 2 weeks, where they commit to building those specific features.
Got it. Focus for 2 weeks.
During the sprint, developers write the code, and, as we just discussed, they commit their changes frequently to a shared Git repository.
Okay, codes in Git. What happens next? Is it magic?
Not quite magic, but automation. That commit usually triggers the CI part, continuous integration. A build server like Jenkins or GitLab CI automatically picks up the new code.
And does what with it?
It builds the software, compiles the code, packages it up. But critically, it also runs automated tests. Unit tests first to check individual components. It might also run code quality checks using tools like SonarQube, looking for bugs, vulnerabilities, or bad coding practices.
So it checks if the new code breaks anything or is low quality.
Precisely. If the build or tests fail, the pipeline stops, and the developers get notified immediately to fix it. Fast feedback.
Okay, assume it passes, build successful, now what?
The successful build artifact, the deployable package, is typically stored in an artifact repository. Then comes the CD part, continuous delivery or deployment. The artifact is automatically deployed to a series of testing environments.
Not straight to users.
Oh, definitely not. First, it might go to a dev environment for initial integration checks. Then to one or more QA environments, QA1, QA2, where the quality assurance team performs more thorough testing integration tests, end-to-end tests, maybe performance tests.
Making sure everything works together properly.
Right. After QA signs off, it often goes to a UAT environment, user acceptance testing. Here, actual stakeholders, like the product owner or business users, can interact with the new features in a production-like setting to make sure it meets their requirements and expectations.
Final sanity check by the people who asked for it.
Exactly. Once UAT is approved, the build is typically marked as a release candidate. Then, depending on the company's process, it's either deployed manually on a schedule, or in a full continuous deployment setup, it's automatically pushed to the live production environment.
And then, fingers crossed.
Well, hopefully all the testing caught any major issues. But yeah, once it's live, monitoring is crucial. Site reliability engineering, or SRE, teams use sophisticated tools to constantly monitor the production system's performance, error rates, and overall health, ready to react if anything goes wrong.
Wow. That's a lot more steps and checks than just coding and hitting save.
It's a rigorous process designed to deliver changes quickly but safely and reliably. Automation is key to making it efficient.
Okay, and underpinning a lot of that modern deployment, I keep hearing about Docker and Kubernetes. They seem fundamental now.
They absolutely are. They've revolutionized how we package, deploy, and manage applications, especially in the cloud and microservices world. Let's start with Docker.
What's the core idea of Docker?
Docker is all about containerization. The core concept is the Docker image. Think of an image as a lightweight, standalone, executable package that includes everything needed to run a piece of software. The code, a runtime, like Node.js or Java, system tools, libraries, settings, everything.
So it's like a self-contained bundle.
Exactly. And then a container is simply a running instance of an image. When you run a Docker image, you get a container. The key thing is that containers are isolated from each other and from the host system. They run the same way regardless of where you run them on your laptop, a test server, or in the cloud. It works on my machine, becomes less of an issue.
That sounds incredibly useful for consistency.
It's huge. Then you have a Docker registry, like Docker Hub. This is a central place to store and share your Docker images. You build an image, push it to a registry, and then anyone else, or your deployment pipeline, can pull it down and run it.
Like a library for these software bundles.
Yep. Two other important Docker concepts. Volumes. Since containers are ephemeral, they can be stopped and started, maybe replaced in the place. You need a way for data to persist. Volumes allow you to map a directory inside the container to a location on the host machine or manage storage, so your data lives on even if the container disappears.
Crucial for databases or user uploads.
Definitely. And finally, Docker Compose. This is a tool for defining and running multi-container Docker applications. You can describe your entire application stack, maybe a web server container, a database container, a caching container in a single file, and bring it all up or down with one command. Great for development and testing.
Okay, so Docker handles packaging and running individual containers or simple stacks. Where does Kubernetes fit in? It sounds more complex.
It is more complex, but also much more powerful. If Docker is about creating and running containers, Kubernetes, often shortened to K8s, is about orchestrating containers at scale. It manages the deployment, scaling, networking, and health of potentially thousands of containers across a whole fleet of servers.
Orchestration, like a conductor for containers.
That's a perfect analogy. In a Kubernetes cluster, you have nodes, which are the actual machines, physical or virtual, that run your applications.
Worker machines.
Right. And your applications run inside pods. A pod is the smallest deployable unit in Kubernetes. It's typically one container, but can be a small group of tightly coupled containers that need to run together, sharing resources like networking and storage.
So nodes run pods, and pods contain containers.
You got it. And managing all these nodes and pods is the control plane. This is the brain of the Kubernetes cluster.
What's in the brain?
Key components include the API server, which is the front door for all communication, how you interact with the cluster. There's the scheduler, which decides which node each new pod should run on based on resource availability and other constraints. And there's etc., a highly reliable distributed key value store where Kubernetes keeps all its configuration data and the desired state of the cluster.
So the control plane watches everything and makes sure reality matches the desired state.
Exactly. If a node fails, the control plane detects it and reschedules the pods that were running there onto healthy nodes. If you tell Kubernetes you want 3 copies of your web server pod running, the control plane works to ensure there are always 3 running, scaling up, or replacing failed ones as needed. It handles self-healing, scaling, rolling updates, service discovery, load balancing, all the complex tasks needed to run containerized applications reliably in production.
Wow. Okay, Docker for the packaging, Kubernetes for the large-scale management and automation.
That's the essence of it. They work together beautifully and are foundational to a lot of modern cloud-native infrastructure.
All right, one last area. We've talked about building and deploying systems, but what happens when things go wrong in production? Say, a Linux server is suddenly slow, or some process is eating all the CPU. How do engineers figure out what's happening?
Troubleshooting and observability on a live system. Yeah, engineers have a toolkit of command line utilities they rely on heavily for this, especially on Linux.
Like digital detective tools.
Pretty much. If the whole system feels sluggish, a common first step is vmstep. It gives you a quick snapshot of overall system activity processes running or waiting, memory usage, especially swapping, block I/O, disk reads writes, interrupts, and CPU utilization. Provides a broad overview very quickly.
So, a quick health check. What if vmstat suggests maybe the disk is the bottleneck?
Then you'd probably dig deeper with IOstat. This gives you more detailed CPU statistics, but crucially, detailed input-output stats for your disk devices. You can see things like how busy each disk is, average wait times for I/O requests, transfer rates. Helps you confirm if you're hitting disk limits.
Okay, what about network issues? If the application feels slow talking to other services?
For network sleuthing, netstat is a classic, though sometimes is preferred now as it's faster. Netstat can show you all active network connections. TCP, UDP, listening ports, Ethernet statistics, the IP routing table, network interface stats. Invaluable for diagnosing connectivity problems, checking if services are listening correctly, or looking for unusual network traffic.
See who's talking to whom.
Exactly. Another incredibly useful tool, especially if you suspect a process is stuck holding onto something, is ULSOF. It stands for List Open Files.
Files, like text files.
Well, yes, but in Linux, everything is a file. So OLSOF shows you not just regular files, but also network connections, sockets, pipes, devices, basically any file descriptor opened by any process. You can see which process has a specific file open or which process is listening on a certain network port. It's fantastic for figuring out resource contention or misbehaving processes.
Okay. See what resources are actually in use.
And finally, if you've identified a specific process that seems to be causing trouble, maybe using too much CPU or memory, you can use PIDStat. You give it the process ID, PID, and it will report detailed statistics just for that process over time: CPU usage, memory usage, I/O activity. It lets you really zoom in on a potential culprit.
So VMstat for overall, IOstat for disk, NetStat for network, LSOF for open resources, PIDStat for specific processes.
That's a good summary of the core toolkit. Mastering these tools is essential for any engineer managing Linux systems. They are the first line of defense when things get weird.
Fantastic. Okay, we have covered a lot of ground today. We really journeyed through the foundational layers, didn't we? Starting with how data is ordered endianness and that crucial memory hierarchy balancing speed and size.
Right, from registers and caches right down to remote storage, and then how programs actually get loaded and executed, that whole dance the OS performs.
Then we move to how systems communicate, demystifying stateless HTTP with cookies, comparing the API philosophies of REST versus GraphQL.
And clarifying those vital roles of reverse proxies, API gateways, and load balancers managing all that traffic.
We dove into building resilient systems, tackling cache problems like the Thunderherd and cache penetration, and exploring solutions like Bloom filters and circuit breakers.
And looked at database scaling strategies beyond just bigger servers indexing, materialized views, replication, and sharding, using Figma's Journey as a great example. Plus, understanding disaster recovery through RTO, RPO, and strategies from backups to hot sites.
And finally, we peeked into the developer's world. He gets 4 storage locations, the CI/CD pipeline taking code to production, the container revolution with Docker and Kubernetes.
And finished with those essential Linux observability tools like VMstat and DILSOF for diagnosing live systems.
You know, understanding these underlying mechanisms, it really does more than just demystify the tech around us. It empowers you, the listener, to think more critically about how systems are designed, why certain choices are made over others.
Absolutely. And that brings us back to trade-offs. This deep dive really highlighted so many of them.
It really did. As one of our sources put it so well, if you don't know trade-offs, you don't know system design.
That's spot on. Every choice has consequences.
So, here's something to think about. When you consider a new technology or system, maybe something we discussed today or something you encounter next week, which of those fundamental trade-offs stands out most to you? Is it cost versus performance? Reliability versus scalability? Maybe performance versus consistency? Or security versus flexibility? Development speed versus ultimate quality? Which balance seems most critical and why? It's always about the choices, and hopefully, now you're a bit better equipped to see them.
Like and subscribe.